another Kent seminar. Today our speaker is in the last minute. Scott really stepped up and then agreed to give this seminar. We had a last minute cancellation, so we had to change our plans. Luckily Scott's presentation was ready to go. And Scott is, just to introduce for those who doesn't know Scott already, as he received his bachelor's degree from here and in 2014, and then he joined Dr. Tutumlaya's groups as a master's student. So when are you finishing, Scott?
Next May.
Next May.
Not this May, but
Perfect. As for those who doesn't know, Scott is working with this giant permeability device with the NPF. I believe his talk today is going to be about this permeability device. His presentation title is Railway Ballast Permeability Preliminary Laboratory Test Results. Let's give him a round of applause and get the presentation started.
Thanks, Dr. Ozair. So this presentation is also exactly the same that Professor Tutumla will also be giving today in Columbia and for JRC, and just so happened it lined up well with today's presentation. When people ask me what I do in grad school and research, I try to keep it simple, and I usually just comes out saying I run water through rocks, and I also crush rocks. So that's exactly what I'm going to be talking about today. Running water through rocks, specifically railway ballast. And I'm just going to introduce to you railway ballast if you're not completely familiar with it, and then talk about the history of testing it, and then go through our apparatus, and then our results. Here's what ballast is. Crushed rocks come straight from the quarry, pretty uniform gradation when it starts out, and it's used to support the track, railway track. And not only does it support it and is a foundation for the railway track, but it's also critical that it drains well. Just like on a road, puddling water on a track is not good news. The railways don't like that. It causes instabilities and unlevel railway profiles. But it's a rock and it breaks down over time. So you can see here, this is fairly new ballast, and this is over time the breakdown of the ballast. And so when it clogs like that, we call it being fouled. And this is pretty well fouled ballast. And the way to quantify that in the field and in the industry is that they say it has a high fouling index. And that just means you add up the amount of material that passes the number 4 sieve and the number 200 sieve. You add those two together, the percents, and you can break it down by clean to highly fouled. So if you have a fouling index of 0, that's perfectly clean ballast. If you have a fouling index like 50 or something, that's pretty much sand. You're driving your trains on sand. You will have larger particles in there. And also, this is a picture from Maziar's work. For scale here, this is a 1-inch sphere that he uses to calibrate his images. And so most of the largest nominal size of the particles is around 3 inches. And I'll show you the gradations a little later, but they're predominantly coarse-grained, large sizes like that. So now that we have this rock, let's characterize how permeable it is and how water flows through it. The first person to do this, you've probably heard of, Henry Darcy. He came up in your geotech or fluid mechanics class. Back in 1856, he tested sand. And he was testing it in a vertical pipe. And these are the results he got. Just to refresh, if you're not familiar with this terminology, so hydraulic gradient is just head. And let me, right up here, so you got a, well, do we have an eraser? Is there an eraser back there I can use? Thank you. You can just think of hydraulic gradient as head, essentially. It's just a normalized, dimensionless value that we can use to say head. But I is just the change in head over the length between your head measurements. So I'll show you a picture more clear what that is on the next slide. But this just means as the amount of water that builds up in your ballast or your sand, the greater your velocity is going to be flowing through it. So the more water pressure, the more velocity. Makes sense. But the other key thing to this graph is it's not just getting bigger, it's increasing linearly. And that was the major finding from Darcy. And that slope is your hydraulic conductivity. So everything that you're using in your models or in your design for permeability of any kind of soil, it's saying that this relationship is linear and the slope is K. All right. So from 1856 now to 1990, we're looking at a study on railway ballast. Connecting this, how does this concept that Darcy found apply to railway ballast? And the first or the most comprehensive study that is out there, or that has been performed until recently, it was by Brian Parsons at the University of Massachusetts at Amherst under Professor Seelig, who's a big name in the geotechnics of the railway industry. And they did a very similar thing to Darcy, a vertical pipe. They put ballast. And one thing that is different, though, is they started the water here and they let it fall. Whereas Darcy would build up the head to here and keep it here and then measure the flow rate coming through over a certain time interval. So it's two different setups. However, Parsons also found for clean and fouled ballast this linear relationship. This is the pretty much exact same graph I just showed you for Darcy, except now it's for ballast. And the things to check out on this graph are we're starting at really clean ballast here with the FI equal to 1%. So naturally you have a greater flow going through there. And then as we increase the fouling index, we're taking it down, we're having lower and lower flows. The other difference here is that they only tested from gradients of 2 to, I don't show it on this graph because it's for another test, but he tested from 2 to 7, whereas Darcy went from 0 to 20. So Darcy covered a much greater range in head ranges on his sample. All right. So very heavily cited source in the railway geotechnics industry or research area is Seelig and Waters 1994. And everybody references this when they talk about permeability of ballast. And these are the values that Parsons got. So Parsons was Seelig's student at the University of Massachusetts Amherst, and now he wrote this book which included this master's thesis work. So here's the hydraulic conductivity values that Parsons found. He puts them in millimeters. However, most publications, when they publicize the hydraulic conductivity values, it's in centimeters per second. So for clean ballast, basically what they found is it's in the range of 2.5 to 5 centimeters per second. And if you look on the order of magnitude scale of things, this is actually at the lower end of a gravel. So we'll keep that in mind. But then he also increases the fouling index. So the more fouled you get, the smaller your hydraulic conductivity. There have been a few other studies, but literally this is all of the studies that have done permeability tests on ballast. And in the grand scheme of things, it's not very many. It's not much to go on. And Parsons was the only one to graph V versus I. All the rest of these tests or studies cite Parsons. They say the relationship is linear, and therefore we just test at one gradient and get our hydraulic conductivity at that gradient. So to show you that graphically, these other studies have said, well, we're just going to test here, get our velocity here, and we'll calculate the slope right there. We don't test all of this to see if it's linear. We're going to assume it's linear, or we're going to cite Parsons because he found it was linear and do it that way. And what else here? So, but some of these studies don't even specify the hydraulic gradients they tested. And then others, we have ranges from 1 to 7, 1.5 to 7, 3, less than 1. And then they find hydraulic conductivity values ranging from 0.032 all the way up to 31. And it kind of depends on which one they're testing. Some people test clean, some people test fouled, and some people test both. And these are all pretty recent. So 1 year before Parsons did his work, there was another PhD student also doing his work at Massachusetts, and he did a flow net on a computer and found that the hydraulic gradients, so the I values, range in the field in a track bed. This is a model of a track bed shoulder. They range from 0.1 to 1. So you can see here, Parsons is testing 1.5 to 7, which from Cole, that doesn't exist in the field. Raman tested in less than 1, although those were uncontrolled. He couldn't really control it. These are greater than what's in the field. These are in the range. Those were also uncontrolled. So nobody is able to, or very few are testing within the range that are present in the field, and very few actually control the gradients of each test. So that. I've just summarized for you the findings of the literature review of all the past history on permeability tested ballasts. And that's basically it. There's really not much that's happened because most people cite Parsons' work. And Parsons was pretty comprehensive with his study. Okay, so now moving into types of permeameters. Like I said, Darcy used a constant head. Parsons used a falling head. And for constant heads, we have a constant head permeameter here. That's what I'm going to be talking about. And this is typically what you would find recommended as a setup for a constant head permeameter. This is all really complicated and everything, but the main thing to take from this is just say the flow comes in vertically, down and out, and you measure the head difference with taps going into your sample here. And it's the same thing that is done down in Australia at the University of Wollongong. They have their ballast here. They have a piezometer taps here. They measure the head difference divided by the length between the piezometers, and that's your gradient, like I said over here. So yeah, I'll explain that. So the gradient now I can show you is the change in head between the water head between these 2 points divided by the length between those 2 taps. All right. So our constant head permeameter we call the University of Illinois Constant Head Aggregate Permeameter UI-CHAP. That was what was come up with. So this was built back in the 1980s, used here, tested pavement subbases, and it was refurbished by Mike Winnick in 2011 for testing ballasts. This is what it looked like when Mike was finished, and now we've made a few additions, which I'll show you. Yeah, well, this is a good thing. So it's called a constant head permeameter because the water level here and the water level here for one flow rate stays constant. This doesn't move. And the nice thing about this is, though, we can change that level by changing how much water we pump into the system. So we have all of our water sitting down here in the tub, and we pump it up through this pipe into the upstream tower, as I call it. And the water builds up, and depending on the resistance of the ballast, it reaches some constant level. And it stays at that level once it reaches a constant flow rate. So it'll stay here and it'll stay here. And so that difference in height is the head difference. And let me also write this down. You've probably seen this before too. Q, the flow, equals K, I, A. So we said that I was delta H over L. We have delta H. We have L. A is just the area of the sample, the cross-sectional area of the sample. We have that. That's 1 foot square. And Q is found using this V-notch weir. And I have a picture a couple slides forward. But this V-notch weir is how we calculate Q. So knowing that, we can back calculate K. That is assuming K exists. Because remember, K says that V versus I slope is linear. Everybody with me? So it must be a linear relationship. So by doing it this way, we're assuming that that slope is linear. So the work that I've done in my master's is verifying the working order and condition of the UI-CHAP and conducting some preliminary tests on different materials, including sand, ballast, and clean and fouled ballast. So this is the V-notch weir I was talking about, and it's literally just a V. And the bottom of the notch is down here. The water flows over it. If you know the height of this water, then you know the flow coming through that weir. And I checked our equation to see that what we're calculating is what's actually flowing over this weir, because we're using the ASTM equation. There's an ASTM standard for flow over a V-notch weir, and they require, the area of the volume of water behind your weir has to be so wide and has to be so long, and the V-notch weir has to be this big above the bottom, and your stilling well where you take the height measurement, it's got to be, a bunch of geometrical requirements, and we don't meet all those requirements. So I wanted to see if this equation was correct for what was flowing over our weir. And as you can see here, I'm just graphing the flow with the height above the bottom of the notch, and as you increase the height, you have more flow. And I plot it at the same points for the measured flow as with the equation, and it lines up right on top of it. So that told me that our weir the equation we were using for the weir was good. It was very accurate. And you can see over here, when we have really large flows, my measured point in the blue deviates a little bit from the rest of the curve. And if you can imagine, at really high flows, I'm just using a bucket to catch all the water, and I'm taking that over a time period. I'm stopwatching it. So I take the flow over stopwatch. Well, at that high of a flow rate up here, it fills up the bucket in 2 seconds. So it becomes less accurate as you come up here. But the equation stays consistent with the rest of the curve. So we stick with the equation. So that was one check I did. And then this is the start of another check that I've been doing for a little while now. And that is, we originally had the pipe entering the water just as an open PVC pipe. It extended down, and it just opened. The water comes in and flows in, and then it's allowed to build up. Okay. And then also you should note here, this is a surveying rod that we use to take the measurement of the water level height. In the increments of this rod, one of these marks is 1/100th of a foot thick, so it's 0.12 inches. So the smallest difference in height that I could take was 0.12 inches, and that's larger than what the water level is actually moving at some points. So I needed a little bit better of a measurement there, like millimeters would be great. And so I'll talk about that coming up. But just keep in mind that's what we're using to measure the water level here. So here I show the rulers, or the surveying rods, and let's see here. So I would take my measurements, plot the data, and I just put in here my reference for, if I start plotting at x equals 0 and move across to 53.4 inches, because that's how far they are, where I'm taking my measurements. I have my flows, and then I can plot. So this is the same thing. This is horizontal distance x that I just showed you, and this is the water level. This is literally just where the water level is in my permeameter here. It's just the same thing. You're just looking at it on a graph now. So, but I'm plotting it over different flow rates. So I'm starting at a flow rate of 0 down here. So give you all a little brain check here. If we have, let's see, who am I going to pick on? Wen-Ting. If the water level is higher over here than over here, which way is the flow going to go? Right. It's going to go this way. Right. So if the water level is higher over here, she said, then we should have flow going this way. Well, what's happening here, Wen-Ting? Which side is higher?
Well, for the largest flow, the left is higher.
Right. So at low flows, we were seeing it was relatively flat. And these are also in very small increments. These are in inches. And the difference here between side to side, so we can consider this basically flat. And then it starts to increase a little bit, but at really high flows, at almost half a cubic foot per second, we have this negative trend. This is a half-inch difference almost. And that is not just variability with measurements. That's a significant difference. So that sends up a red flag. It says, okay, something is not working correctly here. Because if this side is higher, we should have flow going this way. And when I'm standing there running the pump, we have it's like the same thing as you turning on 5 bathtubs and letting it flow. That's how much water we have flowing this way. So it was definitely flowing this way. That's what I'm saying. So that was red flag number 1. And it turns out, okay, so this is just another way to look at it. This is the head difference, and this is the flow. So the head difference should always be positive. So that just means we have a higher head on the right side than on the left side. So this is just showing how much it was changing at the highest flow rate. So to fix this problem, I talked to some TAM professors and some of the hydro folks back at the hydro lab, and we came up with this as a possible solution, a quick fix for now to see if it worked. It's basically just transitioning the PVC pipe to a larger 6-inch PVC pipe with 1/2-inch diameter holes so that the water could flow out of here and swirl around and kind of dissipate that extra energy. So what was happening here is there's extra energy being added by the pump, causing the downstream side to raise higher than the upstream side. So if we dissipate that extra momentum, the vertical velocity of the water coming in and jetting through the channel, then hopefully we could bring down that level to something more reasonable that you would expect for just gravity-driven flow. So it turns out we did that. At the same time, we also installed some piezometers, and with millimeter readings, which is much better than the 100th of a foot that I was saying earlier. And they are installed right on the ends of the sample. So we hook them up to this part of the channel so that now we're taking the readings right on either side of where we'll put a sample. So now this is what it looks like today. So we have these piezometers put in right here and here, and now we have new X values because now we can plot the water level all the way across here, and that's what this looks like now. So today this is what it looks like. This is just an open channel. There's no sample in there, and the water level starts out here, comes down into the channel where we have a reading at the piezometer and another piezometer, and the difference here is essentially 0, and which is good. I mean, that tells us that the losses due to friction are basically negligible. So we don't need to take those into account when we're actually making hydraulic conductivity calculations. So this is good. And these little error bars here show you the fluctuations in the water level, the max and the minimum water level readings. And what we do is I just take the average, and that's where we put the hydraulic grade line, as this is called. So we started at a higher level and end up at a lower level. And it does change for lower flow rates. And this difference here where it goes up, I would say, is a main problem of using those surveying rods because they're not as exact as the piezometers. You can see the piezometers, we can get millimeter resolution with the piezometers, whereas I'm taking them in 100th of a foot at the surveying rod. So it's just not as exact. So this actually could be about at the same level as this piezometer reading. But overall, we're seeing a much better trend. It's not like the extreme 1/2 inch of rise of water that we were seeing before. So it seemed like the flow diffuser has made an impact. And this is for a clear channel. So now that we're more comfortable with how the channel is acting by itself with no sample in there, we say, okay, let's take it to the next step, put a sample in there, see what kind of results we get. And that's the results I have for you today. The materials we tested are ballasts that Michael Neck used, and in his thesis, they were designated as ballast 9 and ballast 14. These are relatively clean ballasts, the fouling index of 1.6 and 3.1, so pretty clean, hardly any fines. And then I also engineered a gradation for a field sample ballast as a fouled ballast, and that has a higher fouling index of 7.4. And then also, just to get our bearings straight and so we could directly compare it with well-established tests, we also tested sand. And we could compare that directly with Darcy if we want. Sand from right out here on the Atlas storage supply. Here are the gradations for all the materials we use. The general trend here is as you're clean ballasts are located over here. They're coarser grain, makes sense. And then as we increase the fouling index here, we start moving this way on the curves, where the loose sand is by far the finest, pretty well graded material. And then I also have included some of Parsons' gradations here too, because we're going to compare our results with some of his results. This is some pictures of the ballast we use. This is the clean ballast, like I said. See, you can see hardly, basically zero fines. 0% passing, or very little percent passing the number 4 sieve and the number 200. This is a basalt ballast. This is a rhyolite ballast. Again, not much fines, although you can see it does have some smaller particles in there. It's also has a different angularity and elongation ratios. These are a little more symmetrical. These are a little more elongated in general. Then this is the ballast that I engineered the gradation for. It's more fouled. You can see there's a lot more dust. And this was field sampled. So you can see it's got a little orange. These are spray paint marks from when they marked something in the field. And then they came back later and took the sample, and that's what we have. And then here's the sand we tested. This is the sample box we use. This is a permanent part of the box here. It's a mesh, a wire mesh. It's on both sides of the box. The water flows this way through the sample. But then when we have finer grained samples that we put in there, we put it on a geosynthetic. And we were concerned that this would get clogged, and we didn't want to test the permeability of a clogged filter. We wanted to test the permeability of the actual sample. So we went through J.P. Giroux's design criteria. J.P. Giroux is kind of the father of geosynthetics in a way. And he has a paper that describes additional criteria that builds on Terzaghis criteria for filters. And so these are the 4 criteria, and he also applies them to geosynthetics. So in the end, we went through that criteria, picked, well, this is a picture of me putting a sample in. We used these foam pads on the sides to keep water from running by on the sides and on the bottom. But, oh shoot, it's not in there. Well, I'll just say it then. We picked the filter. It was a Carthage Mills FXM85, I believe. And I had the data on here from it. It's not super critical, but I had it in there. Okay, so before we actually test a sample, we've tested an open channel. Now we want to see what the losses are from just an empty box. Because there, as you can see, there are still losses from an empty box, mainly because of this mesh here. So when we run an actual test with a sample, we subtract out this loss because we don't want that loss to go into, this is our loss, our head losses. We don't want that to be used in our head loss for the sample because the box is creating that just as artifact of the box itself, not the sample. So we did the same thing, tested at different flow rates, got the loss across the box, and we can use that to subtract out when we actually put a sample in the box. This is the hydraulic grade line for ballast 9. This is a clean ballast. And you can see we have a much larger head loss. Head loss being the water level over here is much lower over here than over here. So there's a much greater drop. That's right. That's just what I mean by head loss. This is the other clean ballast. Again, pretty large head loss. And this is the fouled ballast. In general, still the same trend here. Got a lot of head loss. And then here's the sand, by far the most head loss. So what we do is we now take this difference and then plug it into delta H over here and then divide it by the length between the piezometers. And that's how we calculate I. And we use it in this equation. So this just gives you a graphical representation of different flow rates and different I's that we are able to test over. And so one thing that's really nice about our setup is we can control this. We can set this water level to whatever we want. And that is pretty rare. You can't do that with most test setups. Even with like the ASTM setup with our constant head permeameter, it's more difficult to do that because you have to add on the height to the water without, and you can do that very easily with our setup just by increasing the flow rate of the pump. So this is like the same graph I showed before, head losses with flow rate. And this is the same graph where we had a very negative trend before. So now we'll just break it down here. We have the clear channel. There's nothing in the channel. We essentially have 0 head losses. So that's good. That means just from the friction of the channel, it's negligible. And then we put the empty box in, and as we increase the flow rate, the head difference increases a tiny, tiny bit. So we'll subtract out that tiny bit when we calculate our hydraulic gradients. Then we put in the ballast, and we get these head losses. And we put in this ballast, and we get these head losses. These are both clean, and that makes sense. You would expect smaller head losses for a cleaner ballast. It's more permeable, so it's not going to create as much head difference. Then we have the fouled ballast, and immediately with the fouled ballast, you see we can't even reach higher flow rates because it's less permeable. Makes sense. And we also have much larger head losses for the same flow rate as we had before, so makes sense as well. Then the loose sand is even more so, greater head losses. So all of this is looking good. It's making sense. So finally, we get to the same graph that Henry Darcy did, where we can now compare our results and see if this slope is linear. And what do we have? It's not linear. So let's break it down again. We have loose sand on the bottom. That looks pretty linear. Then we have fouled ballast, clean, clean. Or I should say clean and more clean. So it looks like there's still something wrong with our sample or with our setup, or maybe a linear relationship does not exist for ballast, which has previously been found to be linear. So, and actually there also have been other studies on aggregates where the trend is nonlinear. So now we're going to compare it to Parsons data. This is the graph I just showed you, and now we've added on Parsons. Like I said, Parsons tested these hydraulic gradients that are higher, but he has much smaller velocities going through the ballast at this point, and they're linear. While we have much larger velocities going through, and they're roughly nonlinear. I mean, you could fit a linear curve to it and get a R-squared value of around 0.95. But I would say this is a significant difference, especially if you were to continue testing at hydraulic gradients. This curve would extend way up here. So whatever is being calculated to flow through your ballast with Parsons data is much smaller than what we're finding to flow through it. So this is a big difference. And if you were to fit, like I said, if you were to fit a linear line to this plot and calculate the slope of that line, which would be K, you would get these values. Loose sand of 0.5, fouled ballast 1.8, 16, and 29 for the ballasts. And these values, especially for the clean ballast, is around 30. Well, that's exactly what some recent studies have found for clean ballast as well. So we do match with the recent studies, but not with Parsons data, which seems to be like what the whole industry has used. This also just shows the hydraulic gradients we tested at and the fouling index. So also makes sense. The lower the fouling index, the greater the permeability. So from our literature review and all this work that we've done, the data out there and the studies that have been performed greatly lack data, and just the amount of data out there and tests that have been performed on this are pretty low compared to if you went to some other sector of civil engineering. Not very much is out there. So we have a great potential here to fill in this data gap, as well as the results we're finding are different from what have been found before by Parsons. That being, we're not finding a linear trend, we're finding a nonlinear trend, a power curve. And right now we're speculating that this could be due to a different equipment, but a part of the process of a falling head test is that you assume a linear relationship to exist. So it could be just the methodology and theory behind a falling head test is already assuming a linear trend. So it could be that too, but at this point we're still checking ourselves to make sure that all of this is correct. And with that, I would like to thank everybody that's helped me. The hydro folks down in the by Newmarket in the hydro lab, Isam, and the grad students here that have helped me in the lab, and all the staff here that have helped with the brainstorming with Jim and renovations with Mark. And thank you very much.
Do you have any questions?
So when you are putting the material into the channel, are you compacting the material or?
We do compact. We use a vibratory compactor, a roller vibratory compactor. I do 4 lifts and get densities right around where they should be in the field. Yeah. I measure the weight before and after so we know the densities, and those are dry weights. I do it before, I weigh it before it gets all wet. So. Yeah.
I may have missed it. What's the design, what's the part of the design here for the railroad? I didn't catch, why do they specify minimum value that have to be achieved? Or what's
They actually don't. The AREMA specs really don't. There's no way you can measure a permeability value in the field just from like a track inspector standpoint. So they don't say, well, you have to have a minimum this or this. Basically, the track inspector or the roadmaster goes down the line and says, oh, we have very foul ballast here that needs to be replaced. And that's basically how it's done right now. So that's kind of one way that Mazier's research could potentially help, because he's looking into taking a picture of the ballast, quantifying how foul it is, and then correlating that to maybe permeability, and then determining, okay, well, it's not as permeable as we want it, then we could replace it. But right now, no, there's no minimum value out there. They just have ranges from what Parsons' work has done. Yeah?
I was thinking maybe at smaller velocities, the stream is more smooth, and when you increase velocity, you force it some turbulence inside the ballast.
Yeah, it could be that, and that's what we were seeing before. But theoretically, if you're trying to replicate gravity-driven flow, if you're at the same gradient, you have the same head difference either side, whether you're doing it with their setup or our setup. If you have the same gradient, theoretically, you should be forcing the same amount of pressure on either side of that sample. So you would expect there to be similar velocities. Or you would expect it, when I first started these tests, I was expecting, okay, well, this is great because we can test from here to here and we'll just fill it in. And then I got this back and I was very surprised.
Right. Any other questions? If not, I think let's just thank Scott for this excellent
Yeah, thanks
presentation.
for having me.